Hello, this is Dr. David A. Gaitros, Department of Computer Science at Florida State University, and I'd like to welcome you to my undergraduate lecture series on selected topics in computer science. You can find these videos and others at my YouTube channel at the URL listed below, or you can simply go to YouTube and search using Gaitros and FSU as keywords. Now on to the lecture. Introduction Part 2, original slides by Dr. Dave Wally, modified by myself, Dr. Dave Gaitros. What we're going to do now is continue our discussion of computer organizations, and we're talking about chip manufacturing at the time. Chips are made from silicone. Silicone is a semiconductor or non-conductor. And the way that silicon works is that it acts like a switch. Just by itself, it will not conduct electricity, but whenever you apply power to it, it allows electricity to pass through. And the more power that you apply, the more electricity goes through it. Semiconductors therefore can be used to make transistors, which are essentially an on-off switch controlled by an electronic signal. A wafer is a slice of silicon crystal ingot. Excuse me, a die or chip is a portion of the wafer that is an independent component. We talk about the yield of the percentage of manufactured devices, and this has changed drastically over the years as the techniques for developing silicon ingots have improved with the increased performance of computers and manufacturing techniques. So let's look at this. Here we have the process. We have a silicon ingot, which is produced at using. It's actually not pure silicon. It's a combination of silicon and other elements to allow the semiconductor to be made. We get a slice of it, which creates blank wafers. And then there's a multi-step process that goes through actually making the integrated circuits patterned on the chips themselves. Then it goes to a tester, which actually tests each one of the chips to find out which ones are bad, which ones are good. Then it goes to a device that cuts them up, packages them up, puts them into a parts tester, and then ships them to a customer. The reason we talk about this is the transistor count on a chip has been increasing over the years, 40 to 55% a year, doubling every 18 to 24 months. And this is due to Moore's law, but recent articles, and this is dated about 2018, has shown that to be slowing down. We're hitting a wall, and the wall that we're hitting is just the size limitations and the power consumption. Dynamic RAM access memory capacity chips is also increasing about every 25 to 40% a year, doubling every 2 to 3 years. And again, this is slowing down a little bit. Flash capacity per chip increasing 50 to 60% a year. Again, we're seeing this slow down, and disk density is increasing about 40% a year. Again, we're seeing this slow down just a little bit too. Not as much as they predicted many years ago, but it is slowing down. And part of the reasons that they say is because there's not a demand for it. So here we have the benefits of increasing transistor on a chip. We can increase the chips, and that reduces the cost since less material is being used, and the yield size decreases, or the yield as a die size decreases. Improved performance since there's less distance to travel, they run faster. So there's lots of reasons to do it. There is a disadvantage is that it has limited capacity to dissipate the heat. Now, the scale that you see on here is dated as about 2013. That was about 5-6 years ago. The relative performance per unit cost is still increasing. In other words, it's still a good deal, but again, we're seeing a slowdown in that trend. Here we're also seeing the capacity, the number of transistors on a DRAM chip. This chart stays about the same, a slight drop off near about 2017, 2018. It's predicted that we're going to see that drop even a little bit more. Okay. What's the effects? Well, enhanced capability available to users. You get more compute capacity. Led to newer classes of computers that you see. Your smartphone is a prime example of this. Led to dominance of microprocessor based computers rather than the large mainframe server type processors, and allows programmers to trade performance for productivity, which is a relatively new thing. And the nature of applications are changing just because we can do so many different things, new capabilities. Performances are slowing down in recent years. Why? There's many reasons, and we could go into all those reasons. One of them is just you can only shrink things so much. We're getting down to just microscopic levels. The other reason that it's slowing down is because whenever you pack smaller and smaller circuits into a tiny space, it generates heat, and the ability to dissipate that heat is becoming a problem. So there are several reasons why it's slowing down. Well, this is the end of the introduction part 2. Play it over again if you need to. It's just a quick overview of chip capacity. When you get done with this, please go on to introduction part 3.